Syzygy episode 124, Exocomet Excitation. Welcome back to another edition of the Syzygy podcast. My name is Chris Stewart and I am sitting at the table in her office with one Dr. Emily Brunsden. Emily, how you doing?
Hello. I'm well, thank you.
Excellent. Good to see you. This is episode 2 into a series of N in our first ever official series of Syzygy podcasts.
Yeah.
And this whole series is loosely based, structured around the whole concept of exo things.
Yes.
We started last time with a revisiting of Exo-moons, which we'd done all the way back in episode 19. Turns out in all the years between then and now, we haven't really got terribly far, but it was a great episode. But in that episode, Emily, you did just casually mention that there are lots of other exo things that are being researched, exoplanets, obviously.
Most famously.
Exo-moons, as we discussed. And then you just casually just dropped in, and there's exocomets as well, at which point I said something like, sorry, what? Exocomets, that's a thing? That's a thing we can see. So that's what we're talking about today?
Yes,
exocomets.
that is what we're talking about today. And I have to confess, this is something that... You know how you have different parts of your brain and sometimes different parts of your brain don't talk to each other?
Oh, constantly, yeah.
So in the kind of my researchy part of my brain, which is fairly small, but sometimes there, when I'm working on projects with colleagues, I knew, exocomets are a thing. They're quite interesting. We've been studying them for a reasonable amount of time. But my syzygy part of my brain hadn't connected to that and actually figured out, hang on a minute, exocomets are really cool. We should be talking about this stuff.
Yeah, because you only do an astronomy podcast, Emily. We're only constantly talking about. So what should we talk about this week? Anything interesting? No, I'm sure we can find something in the news.
Yeah.
And it's just sitting there right in front of you, like it's low-hanging fruit.
Yep.
Ready to pluck.
Completely did not connect those dots.
All right, well, let's pluck that piece of exo fruit today. Emily, exocomets. How long has this been a thing? What's going on
Well,
here?
do you want to take a stab in the dark? When do you think we've let the cat out of the bag here? We have detected exocomets.
Okay, so this is a real thing. This is not hypothetical.
Yeah, this is not like exo-moons, which is kind of we maybe have.
Yeah.
This is no, we're really confident.
We're really certain of this.
Yeah.
Wow. Okay. So your question being, when do I think we might have done that? Mm-hmm. Oh, geez. I mean, okay. Exoplanets came first. Right, okay.
1997 was the first sort of confirmed exoplanet around a sun-like star.
Okay, so 1997, exoplanets. We're now 2024. So I'm going to say 10 years ago.
So 2014?
Yeah.
No.
No?
No.
Earlier? Later?
Earlier.
Earlier. 20 years ago? Like 2004?
Earlier.
That's, hang on. Even closer to exoplanets, like 1997. Are we talking 2000?
Earlier.
1998?
We knew about exocomets before we knew about exoplanets.
No, that's ridiculous.
Well, 1987 was our first confirmed detection of an
87,
exocomet.
10 years before. But that's crazy, right?
It
Okay,
is
all
crazy.
right. We're going to get there. So let's start with, can we just start with, because this is a thing on this podcast, is sometimes we're not entirely sure what we're talking about. Like, we got into this last time with some of the systems you were talking about with exo-moons. Like, yeah, but I mean, that's really big. Like, is that actually a moon? Can we really, what are our definitions here? So can we start with, Emily, what's a comet?
Right. Well, that's quite easy.
Comet at all?
We've known about comets for a long time.
Sure.
We've got some very famous comets in our solar system, Halley's Comet being probably number one in the charts, but more recent ones like Hale-Bopp, Schumacher-Levy when it went into Jupiter.
Yeah, that was the one that smashed into Jupiter, which was kind of cool.
Yeah. So, and there's been even some recent ones that have been visible in the skies in the Northern Hemisphere. So right about the time of the aurora.
Right?
Yeah.
Did you see evidence of said comet?
I saw pictures of. So
We've all seen pictures, Emily.
Well,
but did you actually go outside and look
I
at it?
have friends that saw it.
Okay, close enough.
No, it wasn't easy. It wasn't like a blazing great comet like Hale-Bopp or things like that. But it was a good one. So comets are typically icy bodies that, quite small comparatively. So we're talking about, a few hundreds of kilograms typically of material.
Small.
Small. Down to, they range a little bit. Somewhere like between a small moon and a meteoroid thing that's hovering around in the asteroid belt. The sizes vary.
Hundreds of kilograms. Mm-hmm. That's not very big.
That's not very big.
No.
Obviously, those ones are not going to be the big, bright, honking ones we see in the sky.
Sure.
They're more like the size of small moons of other planets. They come from the outer parts of our solar system, so way beyond Pluto in the Kuiper belt. Actually, there's loads of, comet wannabes sort of sitting out there, just these icy lumps of stuff.
Potential comets.
Yeah.
Yeah.
But it's only when they get kicked into an orbit that brings them into the inner solar system that they become a comet, because they start to melt at that point.
Right.
And the melting causes these tails that they have that trail along behind them. So you have the nucleus, the kind of the head of the comet, which is the solid bit, and then you have the gaseous trail, which is all the material getting too close to the sun and therefore evaporating.
It's getting all hot and it's just boiling off all of this stuff into a big long tail behind it. And when you say icy, are you talking like ice, like water ice? Is it that? Or is it just ice as in solidified stuff that would otherwise be a liquid?
It's lots of water.
Yeah.
We call them dirty snowballs often because they're kind of ice, a lot of water ice, but also with like particles, dust, bits of leftover parts of the planetary disk that form the rest of the solar system. So there's kind of rocky bits in there as well. There's some CO2 and things like that in there as well. But yeah, largely water.
Why? Maybe a stupid question. I don't know. You're way out there in the Kuiper belt, right? Which is like way out beyond the orbits of the planets. Yeah. Why would there be all of these lumps of ice out there? Like, where's that from?
Well, it's just all the leftover stuff from forming the planets in the solar system.
Right.
So when our star formed the sun, it had this big disk of material, and that disk, the volatiles, what we call them, so things that are kind of gases, things that would be pushed, that are quite light gases, get pushed out. They get pushed out so far into beyond the freezing points, so they start to go from gas to solid, so they freeze. So that's why water's a solid, because it's really cold out there.
Yeah, right? That makes sense.
And so they just sit out there, and then anything that doesn't make it into being a planet is just kind of left there.
Just lumps.
So in some ways, you can think of the Kuiper belt as a bit like the asteroid belt, but much further away and full of icy things.
Right.
Although there's some evidence that the Kuiper belt's more like a sphere, perhaps, around the solar system than a belt. That's where we would expect to find this mysterious planet X, if we ever find it. So,
right,
planet number 9.
Yeah, there might be bigger things out there, but it gets really hard to see.
Yeah,
when
really
it's
hard
that far away.
There's no light out there. There's nothing that's producing light. So even relatively large planets will be almost undetectable because they're not doing anything that will allow us to see them.
Okay. So that's where the comets come from. And until they become comets, they're just sort of hanging out there. But every once in a while, they might get bumped, like literally bumped on a different course, and sends them winging in towards the inner reaches of the solar system.
Yeah.
But they're in orbit around the sun, and so as they come in, they whip around the sun and then fling themselves way back out into the void again. But as they come past, they have this tail coming off behind, which is all of the icy stuff literally boiling off into a gas, and that's what we see. That's the classic comet shape. Yeah.
Comets actually technically have 2 tails.
Right.
Which is quite exciting, because there's always this particular tail that's just the sublimation tail, so the material that's coming off the comet and being pushed away. So that's always pointing away from the sun.
Okay, that makes sense, because the sun is the thing that's making it happen.
Yeah, and it's pushing it. But you also get a particle tail or an ion tail as well. So that is following the comet. That's following its direction of travel.
Okay.
So the sort of the big stuff that doesn't get pushed by the solar wind follows the comet. Anything that gets pushed by the solar wind is pushed away from the sun.
Right. So depending on where it is in relation to the sun and its journey around the sun, it's got like 2 tails, one behind it and one sort of directly radially away from the sun. That's kind of cool.
Yeah.
Yeah. Okay.
And sometimes you can see them in pictures. There's some nice pictures of comets with 2 tails.
Nice. So that's comets, but exocomets.
Yes.
Comets going around other stars.
Yes.
Now, Emily. Sorry, I need to have a word. Comets are very small. Do I need to emphasize that? And we've already talked last week about planets were hard enough.
Yep.
Yeah. And first confirmed exoplanet 1997, and that was a really, really big planet.
Yeah.
Yeah? Because they're the easier ones to see.
Yep.
And that was hard enough. So I'm calling nonsense on this one. It can't possibly be that you were able to, not you personally, but you, the astronomical community. There's no way that you could see a tiny little comet going around some other star 10 years before that. That's just nonsense.
Well, the thing with comets that you have to remember is that it's not just the lump of rock or ice that we're detecting. They've got these big tails.
Right.
And those, we use different techniques to how we detect exoplanets, for example. But, some of them are similar, some of them are different. But it's those tails that give us the clues to their existence or show us that they exist.
All right. Okay. We're going to have to delve down into that. With the tails, how big are the tails? I mean, how far do they go?
Well, it depends on the size of the comet and how close it is to the sun or host star.
Yeah, that makes sense.
Yeah, bigger comet, bigger tail, closer to host star, more stuff coming off the comet. I mean, these things are, most of the ones we're actually going to be talking about today are no more because we're actually seeing their disintegration.
Right. Okay.
So they're falling apart completely and just being annihilated.
I guess that makes them a
star.
little bit easier to see if it's really going to all go. All right. Okay. Well, then take me through it. What was it? What was the first one, and how did we see it?
We know about 30 stars that have exocomets.
Wow. Okay.
Around them, and that's a mixture of really we know these very well and maybe suspected exocomets. There's two different types. You can have the ones that are going around a star, just like exoplanets, or you can have rogue exocomets.
But I thought the whole point of a comet was that the tail comes from the star, doesn't it?
It does, but once you take that object and put it outside of a star or far away from a star, I guess even if it has a very, very small tail, is it? I guess
sure.
It would still
Okay.
be
All right. We're falling into that grey area of what's a definition of a thing, but sure. Okay. Let's go with that.
Anyway, so there are ones that go around stars and there are ones that don't go around stars. Anyway, they're mostly the stars that have these exocomets form a very tight grouping. They're not just any random star that we've seen these effects in. They're all very, very young stars. So that means they're what we call pre-main sequence. So they're still in the process of being born. So they still have big disks of material. They're still going through that whole process. Or they're what we call zero-age main sequence. So basically they've just started this sort of normal part of their life cycle where they fuse hydrogen to helium and sit happily there for a few billion years.
Right. And sorry, did you just say they're all the ones we've seen fall into those categories?
Yeah. So very young systems.
Why would that be? Do those systems have more comets?
Well, it seems that they've got the disks.
Right.
So once the star gets much older, it's usually cleared its disk. All the planets that are going around that star have formed into actual planets. There's not much material left in that solar system. So there's nothing to generate the exocomets, at least in the way that we're seeing them.
Right. Okay.
And they all seem to be around these particular type of stars called A stars. And A stars is a temperature, effectively, classification around about 7,500 to 9,500 Kelvin Celsius.
So that's somewhat hotter than our sun?
But hotter.
About
6,000 for our sun, yeah. So it's kind of two little steps up the rung. So these tend to be our hosts, should we say. Now, exocomets were not initially called exocomets. Right. And this is going to give you the first clue as to how we find them. They were called falling evaporating bodies.
Falling evaporating bodies. Okay. Evaporating, I get. I mean, you described that before when we were just talking about what is a comet, right? So they're evaporating, they're boiling off because of the energy from the sun. Falling. I mean, everywhere we're all falling, aren't we? Isn't that what gravity is? So, okay, explain.
They're falling into their host star.
Into?
Yes.
Not like around or past?
No. And so this is, they're getting too close to their host star and breaking up.
Gotcha.
So they're in some kind of cataclysmic scenario. So this is where we have either cometesimals or planetesimals.
Oh, cometesimal, I like.
Yeah.
That's good.
So mini comets or mini pre-forming planets, they get too close to their host star through probably they were merrily orbiting in some kind of quite close orbit. And then just like the comets in our solar system, they gained some sort of gravitational kick. They ended up on a terrible orbit, basically, towards their host star, and they become what we call star grazers. So they come very, very close to the host star, usually within half an astronomical unit, so half the distance between Earth and the Sun.
Okay.
As a scale. So they're coming quite close to their host star, and then at that point they're just evaporating and they break up, and
it's all too much.
Yeah.
It's all too much for the star-grazing cometesimal.
Yeah.
I love it.
And we've seen this happen in our own solar system because we've seen Comet Shoemaker-Levy do a similar thing in this upper atmosphere of Jupiter.
Right. Yes, because it came apart, didn't it? Yeah. When was that? How long ago was that? Was that in the 90s? 2000? I'll put it as the chapter art for this bit because it was really cool. Yeah, I hadn't quite realized, but of course it's obvious in retrospect. So that broke apart because of Jupiter's gravitational field. Just tore the thing apart, and then it slammed in a bunch of pieces over a period of time into the surface of Jupiter, which is kind of cool. So imagine that, but it's a star.
Yeah. So you've also got a temperature thing with the stars just making you really, really hot as well. It's gravitationally pulling you apart. So what happens is when these the first detections all came through using a technique called spectroscopy. And spectroscopy is all about taking the light that you get from a star, breaking it up into all its constituent wavelengths and studying basically the very intricate detail of all the different wavelengths, all the different colors that you get from a star. We've done this for, very, very long time. What we see is we're very interested in looking at two spectral lines in particular. So spectral lines are formed when you have a star which is making basically all wavelengths, and then the top layers of the star have chemical species in them that absorb little bits of wavelengths, depending on exactly what the chemical species is. So calcium, for example, ionized calcium, has two very, very characteristic wavelengths called the H and K lines. And what happens is the normal light that's in the blue would normally just come to us and we'd see lots of blue light from the star.
Yep.
But at these very specific wavelengths, actually that light is missing because there's some calcium in the atmosphere of the star that's absorbing it.
Right, it's taking it up, which means that when you look at the light that's coming from that star, you've got these two very characteristic lines or wavelengths missing in that spectrum. And we talk about this like from time to time on the podcast. That's like the fingerprint of that element or that ionic species within the atmosphere of the star. You can tell that that's what that is because that's what that does. It absorbs that light.
Those two lines are always at the same rest wavelength, so we can look at them. Now, or you can think about them as gaps in the light continuum. Now, they're not total gaps. There's still some light that comes at those wavelengths. So what we end up seeing is not just like light, black. We see this nice curve down and a curve up. So it becomes a nice, I don't know, how would you call it, a dip that we see. And we know that from the start, we know how to measure that. We're fairly comfortable with the physics involved. What we see and what was detected in the first exocomet host in 1987 was that on one side of that dip, there was a little extra dip.
Oh. So like a dip and then a dip.
So a dip within a dip, if you like, but only on one side. It wasn't in the middle. It was very much on...
So almost exactly the same frequency, just sort of slightly off to one side and not as strong.
Not as strong.
So what's that?
Well, that is... one way you can think about it is almost the shadow of the comet. So a comet has... Exocomets come in. It's come in front of the star from our point of view. It's blocking some of that light, and so we get this extra tiny little dip. And it's almost always redshifted. So what that means is that the dip is from an object that is moving away from us.
Moving away from us. Okay, so hang on. Take me through the mechanics of that. How does that work?
So it's redshifted because when light is moving either towards or away from us, it changes in wavelength or it changes in color.
Yeah, I mean, if we look at a distant galaxy, right, we can see the light from that galaxy redshifted or blue shifted, and that tells us whether or not it's moving towards us, moving away from us. And that's the exact kind of data that told us about the expansion of the universe. So that makes sense. I'm trying to wrap my head around why would...
So the dip, if the comet was going perpendicular to our line of sight.
Yep.
Then,
so across the star.
Yep, it would be bang in the center of the line, and that would be fine.
Yep.
Problem is not problem, but the exciting thing is it's in the red part of slightly to the red side of the line, which means that the comet's not going across, it's going into the star.
Oh.
It's going away from us, but towards the star.
The star, right. Yes, that was the bit that I couldn't figure out as well. So what's the comet doing? Oh, but you said it before. It's going into the star. It's falling. It's falling.
It's an infalling, evaporating body.
That's awesome.
Yeah. And these things are transient. So sometimes you look and they're there. Sometimes you look and they're not. They typically change on timescales of about an hour or two. So they're very exciting things to watch and monitor.
Yeah. Well, I mean, presumably, eventually they actually hit the star and they're all gone.
Yeah, exactly. So, yeah. And then, so they evaporate and then they're gone. And then you've got to wait randomly for the next one. You can't predict. There's no periodicity to these. That's just, does a random comet fall into the star while you're watching it?
So that's how we saw that first one back in 1987. That's exactly what we did. Yeah,
and it is.
And was that like, did someone kind of point at the spectrum and go, wait a minute, I know what that is, and suddenly exocomets are a thing? Or did they kind of go looking for it?
No, I think they found it, and then that was basically the only way you could explain it. The system that this comes from is one we're going to talk quite a lot about today. It's called Beta Pictoris. It's the most famous exocometry system, and amongst other things. So it's actually a very bright star quite close to us that's quite easy to study, and was being studied a lot in the 70s and 80s to do with its disk, because it's got a really cool disk. So we'll come back to that. But yeah, we were looking at it because it's a cool system anyway, and then we saw
then we realised it's even cooler than we thought.
Yeah, exactly.
Awesome.
So that was, as I say, that 1987. Since then, we've got, maybe about 30 of them.
So not quite as prolific as exoplanets.
No.
Not up in the several thousands. But 30 is, like, that's non-trivial.
No, exactly.
We know that that's real.
Yeah. And then since then, of course, we've had the whole field of exoplanets just go bananas, which was very exciting. We got these space telescopes. So Kepler being, of course, one of the most famous high-precision exoplanet hunting telescopes. So maybe it shouldn't surprise us that we actually went looking with Kepler to see if we could find exocomets. And I'm going to tell you this story because I think this is amazing. So just like when we see an exoplanet move in front of its host star, we see a very tiny drop in the light, right? Now, we talked about this last episode as well. If you had an extra little dip, that might be from an exo-moon.
Yeah, I mean, and as we discussed, like that's kind of like a 1% level on top of a 1% level of the amount of change that you would expect to see. Like it's tiny.
Yeah, but for an exocomet, because it's not just the head, you've got this big tail. You've kind of got, if it's aligned correctly, you've got a bit more of a chance. You're covering up a bit more of the star.
Okay.
So you could get actually a bigger dip from an exocomet than you get from an exo-moon.
Sure. Okay. Maybe not an exoplanet, but a moon. Sure.
Yeah. And so this is amazing, the tenacity of this. So there was a group and one actually author of this paper, the paper came out in 2017 about looking through the Kepler data. So one of those authors did a visual search of what's called Q1 to Q17, 4 years of Kepler data for 201,250 stars.
Visual search.
Visual. So
this is not feeding the data into a computer and saying, AI, find this.
No. And it took them 5 months to look at 200,000 plus
stars. Who are these people? Like,
very, very dedicated people.
Like, well done and everything, but haven't you got something better to do this time? Like, that's amazing.
Amazing. Well, I mean, there was obviously some there was some programming behind that was helping pull up, what might be useful things to look at over other things. But it's also a good reminder that you can write a code to try and automatically detect, for example, an exoplanet in your 200,000 stars. But you might not always be looking for the right thing. There might be stuff there that you haven't seen before that you don't quite know what it might look like, but you can have a look for it.
The program's only ever going to be looking for what you told it to look for, whereas when you look with your own eyes and brain, you can kind of maybe adapt on the fly and go, oh, but maybe this one, which is a bit different, but let's have a look at that, which a program's not going to be able to do.
No, indeed. And so they did, and they found a few examples of around a couple of stars, I think initially 2, one which had 6 candidate exocomets. And what was really telltale that these were exocomets, not exoplanets, was the shape of their dips. So a planet is typically a sphere, right?
Yeah.
So when projected onto the surface of the star, it looks like a black circle kind of going across, right? A comet is like a little black circle with a big fuzzy thing behind it going across the surface. Yeah,
it's a very different kind of shape profile.
Yeah, so a planet you'd expect to have a very symmetric drop, come back up, right? It's a curve because of various physics, but it goes nice curve down, nice curve up. You could draw a line through the middle and fold it in half and it looks exactly the same.
Yeah, and we've talked about that many times on this show. There's loads of show art out there from past episodes showing these very characteristic dips. Sure.
Yeah, but a comet, it's got this very condensed head, so you get a very sharp dip down, but then you get a much more gradual rise up as the big fluffy tail of the comet goes across.
That makes sense. So completely different shape of the dip.
Yeah.
Even though it might be a very small dip, you know what you're looking for. Right.
So sharp down, slow back up. And they found 6 or so of these transits of exocomets.
Cool.
So this is working in now photometry, which is the complementary way, a different way of looking at these stars. And as you might expect, following on from that, 2020, 2022, we were able to use tests to find exocomets, not in any new systems, but actually in our good old friend Beta Pictoris, the original comet
Going
host.
back to the OG, yeah.
And we found some nice comet transits in that star now through tests.
Brilliant. It is extraordinary. At the beginning of this, my mental image was that a comet is so small. It's just this tiny thing. There's no chance, but I can kind of see how that works. And it's testament to just how good our telescopes, our machines, our computers, our eyes and brains are to be able to spot that.
Yeah,
that's amazing.
Really cool.
Yeah.
So I think it's worth just having a little bit of a chat about Beta Pic, because it's Beta Pictoris. Beta Pic is a very special star.
Listener, Emily's sitting here with a big grin on her face because this is obviously cool stuff.
It's cool stuff.
It's really nice when someone who is really into something gets to talk about something that's really, really cool. And Emily's just done that. So, tell us a story, Emily.
Well, okay. So Beta Pictoris is actually a star I'm currently working on. And I hadn't made these connections because my colleagues in New Zealand have a Marsden grant, so that's led by Professor Karen Pollard, and who was my former PhD supervisor, actually.
So a very solid connection.
Yes, indeed. And she's leading a research project to look at lots of these systems, these exocomet host systems, but where we're tackling them we're really good at spectroscopy. We've got a really good telescope that does amazing spectroscopy. We're also very good at doing pulsational work.
Right.
And this is going to become important because it turns out that quite a few of these stars themselves are pulsating. So disentangling the signals from the pulsations in the comets, for example, becomes really tricky.
Okay. Now, tell us a little bit about that, because that's your thing, right, is that you deal with, in your actual research, you deal with stars which are not just sitting there being a star. They're stars which are changing, wobbling, pulsating. So just tell us a little bit about that.
Yeah, Beta Pic's a wonderful example of this. So as we said, Beta Pic's a very young A star, and it has these pulsations which are called delta Scuti pulsations. They're named after the first star that we kind of noticed that had these.
I seem to remember we've talked about them before.
Yeah. So delta Scuti pulsations, they come from, it's basically an internal instability in the star. So it works a little bit like a heat engine where you get build-up of pressure and temperature inside the star. That means that it's got nowhere to go. The energy can't get out of the star fast enough, so it expands just a little bit. That expansion causes the star to get less dense, basically. The energy can escape again, and then you get a contraction of the star because it's expanded, it's cooled down, and it contracts again.
And then we start
these things
all
again.
over again. So it's almost breathing in and out. It's expanding, contracting, expanding, contracting.
Yeah, these things are slightly more complicated because unlike a Cepheid, which does literally do that breathing sort of model, they have what we call non-radial pulsations. So there's bits of the star, segments of the star moving in, segments moving out. So they have kind of a bit more complex geometry to their pulsations. But more or less, that's what they do.
Sure. To first order, yeah, that's about right.
Yeah, okay. Exactly. So, yeah, and this, of course, we've talked about before, has effects on the light curves. So the things that we're looking for when we look at transits from Kepler or TESS. So that means that the star has got this kind of variable brightness. So it goes up and down and up and down and up and down and up and down in brightness. It also means that the spectral lines wobble around in space because the surface velocities of the star are changing, basically.
Which I still, again, talking about things that blow Chris's mind, I find it amazing that, we were talking before about red shifting and blue shifting and being able to tell whether the light is coming from something which is moving towards you or away from you. It amazes me that you could see that of the movement of the surface of the star. Like, I tend to think of redshift and blue shift being associated with things which are moving quite fast. And I don't imagine that the surface of this star is moving really fast. But is it?
Well, we're talking about tens of kilometres per second, typically.
Okay. I mean, that doesn't seem hugely fast.
It's not huge, I guess, on the scale of a star.
Planes move faster than that, right?
Yeah, exactly. No, you're right. Yeah, we are very, very sensitive in these techniques.
That is extraordinary. So well done, everyone.
Well done.
Yeah.
Yeah, so of course, both of those things, those pulsations, tend to then wipe out the signals of smaller, perhaps, effects like comets.
Sure.
Or at least make them very, very difficult to disentangle from those signals.
Yeah. There's something much bigger happening, and a comet surely would just get lost in the noise of that. So
we're very good at figuring out what these pulsations are and figuring out how to remove them from data. Whereas the exocomet, I guess people who are coming in from more the exocomet direction are very good at looking at the exocomet signals and trying to model those and figure out what that means about the exocomets that you're seeing. So we're just kind of all approaching this in a slightly different way. And one of our, I guess, strengths is that we can really do good things with the data set to get rid of the stellar pulsations.
Right.
Not something I would normally actually really be doing as part of my work.
But because you're so good at it, you know what that signal is, which means you can remove it.
Yes.
Like if you didn't have a really good grip on what that main signal was, you can't block it out. But because you do, you can.
Yeah.
Right.
So it's quite a fun project for that. But coming back to Beta Pictoris, I mean, this is really the system that has it all. So almost any stellar astronomer in the world will have a vague understanding of what Beta Pictoris is. Okay. It's a very famous star.
It's that famous.
Because it's got everything.
Okay.
It is the hyper mega mall of stellar astrophysics.
What's it got? What are you talking about?
Well, okay. So, the star itself is sort of fairly ordinary in some senses, right?
Okay.
It's quite close, which is nice.
Always helps.
So it's about 64 light years away. So it's not super, it's kind of in a similar region of the galaxy as our sun. Makes it easy to study. It's quite bright. You can see it with the naked eye if you want to. It's a very southern target, so we can't see it here, but from the southern hemisphere.
Hence New Zealand.
Yes, indeed. It's a bit bigger than the sun, about 1.75 times the mass, nearly 9 times brighter than the sun, because this is just linked to the fact it's a lot hotter, so it's about 8,000.
Sure, okay.
Kelvin versus our sun, and it's a lot younger. So best estimates at the moment are that it's on the order of about 20 million years old.
Which is pretty young.
Very
I think,
young.
for a star.
Yeah. Our sun is, 4.5 billion years old. So this is a young star. It's only just come around.
Is it in a region of lots of like young stars, or is it just sitting there?
This is one of its interesting points. So I'm just going to give you the blitz list of all the things you might find interesting.
Hit me
about
with it. I'm ready.
It's got 2 planets.
Yep.
It's got a large debris disk, one of the first observed. It's got belts. It's got rings. It's got an edge-on second disk. It's part of a moving group. It's got pulsations. It's got carbon overabundances in the disk. It's got a dust stream that's heading towards the solar system. And it's got comets.
Who needs anything else, right? We don't need the rest of the galaxy. Just look at this thing and do all the research.
Exactly. That's why no matter what part of sort of stellar astrophysics field you're in, there's probably something for you in Beta Pictoris.
That's awesome. It's almost like, the creator set this one up as this is our test field, right? Mm-hmm. Just do all of your preliminary studies on this one. It's got everything. And then later on, we'll just spread everything else out. But this one, just look at that.
And it's close and bright and easy to observe, which is wonderful.
Almost seems a bit too good.
Suspicious.
Yeah. What's going on there? All right, so take us through some of what the hell all of that means.
So let's start with the planets. Everyone loves a good exoplanet.
Yep, and I think I've got a grip on what that might look like.
Yeah.
But go ahead.
We've got 2 of those. They're Jovian-ish star size, so actually a bit bigger than Jupiter. Their claim to fame is that they are the 2 closest planets to the solar system to have been imaged directly.
Right.
So we've taken pictures of them.
So actual looking and pointing and saying, ooh, planet.
Yeah. Wow. And there might be more. There's some hints that there might be more exoplanets in the system, which is quite cool. Now, the disk. The disk is the very interesting, complex part of it. And it's actually linked to a lot of the things. Young stars will often have disks, but this disk seems to be very interesting, and we can dig into a lot of its characteristics. So as I say, this is the first star that we've observed to have a disk.
Now, when you say disk, this is the material, like going right back, right? You've got big ball of gas and dust and so on. Star starts to form out of that, collapses down. I'm imagining everything's swirling around. Mm-hmm. You've now got the stuff from which the star is made. Anything left over can go into planets and other things. But in the meantime, you've got this big disk of material.
Yep.
That's what we're talking about.
That's right. So the star kind of forms its confined sphere. First, it's left with this disk, and over time, that disk will form exoplanets. Part of the outer part of the disk will freeze off as it gets too cold. Mm-hmm. Volatiles will get pushed out to the outer part, and eventually it will be clear away. Yeah,
which is what we have in our solar system. We've got all the planets. We've got the stuff way, way out. We've got a bit of an asteroid belt in the middle there, but we don't have a disk.
No.
Anymore.
No.
Okay.
So. So the disk is really cool. We have seen belts in the inner part of the disk, so kind of thick bands. It might help to think about Saturn here a little bit.
Yeah, the rings of Saturn, you mean?
Yeah. So the rings of Saturn kind of form bands. So take that kind of idea and now just stick it around a star.
All right.
So you might have bands where you've got gaps. Some of those gaps are to do with the moon, not the moons, it's the moons of Saturn, but in this case it's the planets around the star that are clearing out some of that debris. There's some rings, so very thin bands is another way to think about a ring, right? Very thin.
Yeah.
And the outer edge of the disk.
So it's still the same kind of idea, but very thin. It's almost like you've gone from, thick amounts of material with little gaps in it to mostly gap with little rings, right?
Exactly.
Okay, but same idea.
Yeah. And the cool thing about this disk is it's edge on. So we're seeing it, we don't see it, when we see the face of the disk, we see it traversing the front of the star.
I've got my hand up now and want to ask a question. If you're seeing it edge on, how do you know it's got gaps in it? That doesn't make any sense.
Well, they're not through direct observations. They're through all sorts of things like tracking, some of the infrared things. It's not 100%, so there is a slight tilt to it. We can track some of the it's all through the infrared excesses where those fall. Yeah, I know.
I'll take your word for it, but that just sounds mad.
It's quite cool.
People are incredible.
And it's even got a second disk with a 5-degree tilt to the primary disk.
Right.
Which we don't have a lot of understanding.
How does that happen?
It's very, very faint. Seems to become something that's I don't know. It's either something's come apart or something hasn't quite fallen into the disk.
Right. Because the disk, like when you start with, again, going way, way back, right, you've got big cloud of stuff, which is, for all intents and purposes, let's call it a sphere, right? It's not flat, but with a tiny amount of rotation in a particular direction, that will collapse down to form a star or a protostar, which is spinning in a particular direction. And that, am I right, defines the plane of that disk then.
That's right.
That's what angular momentum does,
Yep.
right? Even a tiny, tiny, tiny amount of excess spin in one direction, that'll take over as things swirl down into it. And that gives the plane of the disk. So how do you get two?
So, it's either a stability that just is still left over, so
Right.
it hasn't quite collapsed down to the main disk, and it's for some resonance reason it's still fairly stable to remain there so long. Or it was another sort of clump of stuff that has kind of broken apart and formed its own
Right. Okay.
sort of secondary disk.
So that's not going to last.
Probably not. No. Well, the whole disk isn't going to last
Well,
either.
yeah.
But so that's kind of the disk. We think some of the gaps that we see in the disk might be to do with another exoplanet interfering, just
Okay.
like the moons of Saturn.
So we've
interfere
seen
with the
two,
rings.
but there could be more.
Yeah, exactly, which is quite cool. What else? We got it's part of the very famous Beta Pictoris moving group.
Well, I mean, we've all heard of that.
So in this a moving group is basically when we look at a patch of sky and we look at the direction that the stars in that patch of sky are traveling. Most of them are traveling almost semi-randomly, right?
Okay.
They're just going off on their thing. But when you have associations, and this is particularly true for young stars, then they all are traveling in the same direction at the same speed. So this happens because when you have a cloud of gas and dust collapse to form a star, it doesn't just form one star. Typically, you'll form on the order of 100-ish stars at exactly the same time.
Right.
And so they start off as quite a tight little group, but then the dynamics of the galaxy just disperse them slowly over time. But you can see remnants of that. So in this case, there's about 17 systems, 20 to 30 stars, because some of them are binaries systems. And they were all born at the same time. So they're all very young, so they're still quite close
Right.
enough that we can say, yeah, you all came from that same place.
And that's what you mean by a moving group, right?
Yeah.
And so they, even though over time they're all moving off in random directions, doing their own thing, because they came from effectively the same place, there's a correlation there. We can see this group doing its own thing, even though all of the stars within it are also kind of doing their own thing.
Yeah.
They're all,
I mean,
they're
if
all
you-
still
if
kind
you-
of correlated.
Yeah, if you figured out where each star was going right now, what its direction of travel is, and then if you imagine rewinding time, they would all come back to the same place.
That's where they came from.
Yeah.
Yeah.
That's quite cool. Interestingly enough, this group also has one of the closest free-floating planets to our solar system.
Okay. How was that spotted?
Pass, but it's in there. Possibly microlensing, but I'm not sure on that
Okay.
one.
Yep.
Yeah, so that's a moving group. Pulsation. So this is, as we said, a Delta Scuti star, which is, quite an interesting type of what we call classical pulsator. It's got two main frequencies of pulsation that were very well measured. One is just over 30 minutes and one is about 37 minutes. So we've got two pulsation cycles. And that's the kind of thing that we'll be delving into as part of our work on this project. To try and
That's your side?
Yeah. To do that, obviously for this star, but we've also got quite a few other stars which look like they might be similar. And we can do the pulsation analysis, cometry analysis and things on those as well. What else? And the other thing that's quite cool is there's a dust stream in this system, which is actually, I say dust in cosmic dust. So we're not talking about like obviously fluffy dust that's caused by dust mites. It's very tiny particles, tens of microns in size. And there's a stream of those coming towards the solar system.
Coming towards
Yeah.
our solar system.
So there's just like a
Right.
channel, a river of these coming towards in our sort of general direction. And we think this is actually the main source of interstellar meteoroids that come into our solar system.
Really? It's kind of feeding them to us.
Yeah.
That's wild.
It's almost like, I guess, a hose pipe that just happens to be pointed in our general direction.
Right. So it's nothing nefarious. They're not trying to do anything to us. It just happens to be, oh, look at that. That's where they come from.
So we're just getting, in our solar system, a lot of these very, very tiny micro meteoroid things coming in, and a lot of them come from the Beta Pictoris system.
That's wild. This system really is trying to capture our attention, isn't it? It's a bit of a show-off. Look at me, look at me.
That is very cool. So all of those things just in one star system, which actually makes it, in some ways, obviously very interesting, but also in some ways very difficult to study.
Why? Because there's just so much stuff going on.
There's so much stuff, and there's so much going on. I did have a look, and between 1850 and 2025, there are now a grand total of, as of today, 1,966 papers.
Just on this system.
66 of them this year alone.
Wow.
So there's a lot of people really interested in this system.
Wow. But does that make it hard to, I mean, you were talking before about how you people who study the pulsating stuff get to then try to sort of subtract that so that the comety people can try to seize their signal. Like, does all the other stuff that's going on with this system, does it all kind of get in each other's way? Like, if you're trying to study one aspect of it, let's say, is there another exoplanet? Does all the other stuff, the disk, the rings, the pulsations, the comets, the stream of micrometeors, like all of that, does that kind of all get in the way? Is it actually just a really messy, noisy signal?
I think yes and no. I think some of it you can compartmentalize off. So, and some of it you just need to work together on. So the exoplanets, for example, don't typically have strong signals in, say, for example, the TESS, or they're not transiting exoplanets like you would see in Kepler and TESS data specifically. In fact, there's been some very detailed studies to look for them in those data sets, and they're not there, even when you use some very advanced techniques.
Okay, so we're pretty sure.
We see them in other techniques, but they're not in those particular data sets. So there's bits you can kind of parcel off and say, well, that is interesting, but it's only relevant to that particular set of stuff.
Sure. That doesn't get in anyone else's way.
Yeah. There's other stuff, though, that you really do have to work together on. So, for example, in this project, we're working not only with, obviously, other pulsation people, but we're working with people who are very familiar with A stars. Mm-hmm. So even more familiar than what I am, for example. It's not the first stars that I've worked on. But we're also working with people who have done comets, cometary models. So it's not like we're sort of all working in rooms by ourselves and then saying, all right, your turn. It's more of a collaborative effort to get down into the signals that we are seeing.
Sure. But I guess my question was more around, like, are there things that people are trying to study which just, if only you people, if only your stuff wasn't there, this would be so much easier.
Oh, sure. I'm sure if you're an Exocomet fan, if that was your primary research interest, then you would be a bit annoyed that you've got, these delta Scuti pulsations.
Right. But at least you've got, you sitting across the room going, I can help you with that. Don't worry about it. Let's talk.
Exactly. Yeah. So then when it comes to the comets themselves, this is the comet system that we know the best. We know a lot about it. In fact, it's many orders of magnitude better understood than anything else. Anything else is almost...
You mean any other exocomet system?
Exactly.
And is that because there's like a couple of thousand or however many it was papers that have been, like, we know this system really, really well?
Yeah.
Or is it just because the exocomets in this system are actually particularly good for looking at?
Well, it's bright and close, which means that there are lots of people studying it. We know lots about it, and therefore the comets are, we're observing it a lot. We're interested in lots of different aspects of it. We've got lots of data. So that's really, it's all connected to that.
Yeah.
Whereas the other stars that we have got some bright stars that we've seen exocomets on, but they're anywhere near as studied as this system. So the comets around Beta Pictoris specifically look like they form at least two, maybe more populations of comets. And this is where we're going to actually come all the way back to close to the beginning of what we were saying.
Circle right back around.
Remember how we said that comets were kind of like these dirty snowball things?
Yeah.
These exocomets are not.
Wait, okay. So, right.
Yeah, so they're
Explain.
actually they're not got the ice We don't think these comets are icy. We think they're just purely rocky.
But isn't the ice bit what makes it a comet, Emily?
Well,
You're breaking my brain here.
Well,
what are you
not
doing?
really. I mean, ice is nice.
Right.
And that ice is what, they come in our solar system, they come with ice because they're coming from the outer reaches of the solar system. Whereas these are just rocky things that are evaporating, right? So rock can evaporate just as...
Guess you get close enough to a star.
Yeah.
Anything's just a form of ice, right?
So the comet's because it's evaporating, not because it's got water or ice.
Gotcha. Okay.
Right?
Yep.
So these are probably very rocky comets that are coming from quite close. Maybe they were in stable orbits quite close to Beta Pic. Something's disrupted them. It could be an exoplanet. It could be just something else, an instability in the disk. They get flung into the host star and they flare up and poof, they're gone.
But how do we know that they're not icy? Because of the spectrum?
Because where they come from.
I see.
Yeah,
okay.
they're way too close initially. Water is not frozen and they're too warm.
You don't even have to look for it. We know it's not there.
Yeah.
Right.
Yeah.
Gotcha.
So where they come from, their origins. But there's multiple populations. They seem to be coming from different angles. Mm-hmm. Some of them are very weird angles. So they're coming at all sorts of strange places. So that's
But this is a young system, right? So that's maybe not hugely surprising. Like there's going to be stuff around.
Yeah, but it's telling you something about the disk, that there might be different places in the disk that they therefore might be coming from.
Okay.
So there's not just one single source, which is quite cool. And this is where the perturbed planet is also linked to some of these as well. So yeah, this is all the cool stuff that we've learned about these specific Beta Pic comets and the things that we therefore want to go and look for in the other systems to see if we can see, do they happen as often as for Beta Pic? Are they coming from a similar distance from the host star? All those kind of questions. And so I think when you came into my office, actually, I was sort of coincidentally working on some of the spectroscopy of Beta Pic itself that we've been taking for a long time, actually, in New Zealand. And I showed you some of those spectral lines. I showed you calcium, actually, H and K. Saw that little extra dip of an exocomet.
Yes, I came into Emily's office and there's data on the screen. There's a graph on the screen, big sort of pointy dip in it. And Emily's going, what do you reckon that is there? I don't know. That, my friend, that is an exocomet. It's like, no way! Really? That's so cool.
Yeah, so the things that I guess the researchy part of my brain was working on, which at the moment I'm working very much on getting our data perfected. You can't get perfection, but at least working on our data, improving the signals that we can get out of our data so that the cometry signals is as strong as possible. That's my current task. That sort of work is going to, eventually feed down the line to this much larger project. And very excitingly, coming up in December this year, we've got our next TESS observation of this star.
Oh, right.
So
nice to know. Tess is still doing its thing.
Yeah, TESS is just carrying on.
Always a favourite space telescope of this podcast.
Indeed. And as I mentioned before, TESS has seen some exocomets in the previous data sets, previous times it's looked at this star, but it's coming up to look at it again, which is even, are we going to see it again? Are we going to get some more precise data from this one? And in fact, the research group has put in and just been awarded literally yesterday what we call director's discretionary time.
Ooh, that sounds impressive.
It's it's very exciting. So it means that normally TESS would be observing it every 5 minutes. So it would take a picture every 5 minutes. That's standard mode. But for a select number of objects within each particular sort of season of observing, there's a short list of ones that can be observed much more frequently. And
you're on that list.
And we got on that list.
Nice.
So we're getting, 20 seconds. Every 20 seconds we're going to get
No wonder you had a big grin on your face when I came in.
Yeah.
That's cool.
It's very cool. So when you're talking about, for example, cometary transits, which are only happening they come and go within an hour, or indeed the pulsations, which have, periods of a few minutes, or 30 minutes or so, having every 20 seconds is going to be
much better than every couple of minutes.
Oh,
which
yeah.
is like, well, we got one. Thanks. Yeah.
Exactly.
That's great.
So we're very excited.
Well, Well, Emily, when I walked into the office, I knew something was up, right? Partly because there was a very cool graph on your computer screen showing some really, really interesting things about exocomets, but also because there's something about the way you were carrying yourself. There's a big smile on your face, and I've got something that I want to talk about, and we now know what it is. That, first of all, what's the name of the system? It's the
Beta Pictoris.
It's a hell of a system, right? That's number one. Number two is you're doing some really cool research. And number three is, oh my God, you get directed discretionary time on tests to study this damn stuff. That is so very cool. So thank you for sharing that with us. No wonder you wanted to do exocomets. It's just amazing that it took you quite so long to come up with that topic.
Yeah, well, the neurons are joined now in my brain, so
who knows what else there is out there. In a couple of episodes' time, you'll probably go, oh yeah, there's this other thing that I do. Anyway, we'll see. Listen, Emily, if people wanted to write in with their own suggestions for directors' discretionary time on a space telescope, how could they get in touch with us? Is there a main way that they could do that?
You should always go to our beautiful website, syzygy.fm, SYZYGY. All
well
the other
done.
syzygies are...
After all this time, you still got that?
Not so useful, Yep. We also have some social media.
We do.
We got some Instagram, we got some Facebook.
Yeah. Just generally at SyzygyPod out there in the world, and you might be able to find us. You never know your luck. But the website's the place to go, where you can find all of our past episodes, and a contact form where you can just send us some hellos, a couple of ideas, tell us how much you love us, that kind of thing.
I can put out a request.
Go on then.
We are now starting to plan amazingly for the York Festival of Ideas.
That's true. Coming up.
2025, which will be
May next year?
June, late May, early June. And what we are the theme for this year is just in our wheelhouse. It's called Making Waves.
As if they saw us coming.
Yeah. So Chris and I could fill a whiteboard with all our ideas about how waves are interesting in astronomy, but it might be quite cool to hear from some of our listeners what sort of waves in astronomy they might think are.
Yeah, that's a really good idea.
Find out about.
That's a really good idea. If you find yourself thinking, this is what you should do, get in touch with us through the website, syzygy.fm. Go and find our contact page and tell us what we should do a live recording at the Festival of Ideas about in terms of waves. That'd be really, really cool. Get in touch. We'd love to hear from you. If you would like to support the show, bunch of ways you can do that. Tell everyone. Tell people that you know and love that there's this amazing thing called Syzygy where they talk about, oh my God, you wouldn't believe there are exocomets. It's a thing. Go and tell them and just spread the word. The more people who listen to us, the happier we are. If you want to become a financial supporter of the show, throw a couple of bucks our way every month to help us keep the lights on and keep the electrons flowing through the website, patreon.com/syzygypod. And we're thankful to every single supporter out there of the show. But otherwise, just keep listening. We'll be in touch again through the podcast sometime soon. We're sort of on a bit of a roll here with this first ever official Syzygy series, the Exo series. So stay tuned. Emily, we'll catch up again really soon.
See you later.
All right, bye everybody.